Welcome back. Today, we're diving into a really cool tool in calculus, the alternating series test. It's built for a very specific but super common type of series, one where the terms keep flipping between positive and negative. Let's get right into it. So, up to this point, we've mostly been wrangling with series where all the terms are positive, right? But what happens when a series just can't make up its mind? When the signs just keep flip-flopping back and forth, plus, minus, plus, minus. Just look at this classic example. It's called the alternating harmonic series. We go up by 1, then we pull back by half. We go up by a third, then pull back by a fourth. This little dance, this back and forth, actually changes everything about how the series behaves, and we need a special tool just for this situation. Now, the official name for these is, you guessed it, alternating series. You'll usually spot them right away because they have that little -1 to the power of n piece. So the first thing you always want to do is mentally pull apart that sign flipper from the rest of the term. We call that positive chunk b sub n. And that's the part we're actually going to put to the test. Okay, so they flip-flop. Who cares, right? Well, it turns out this little feature has a huge and actually really helpful consequence when we're trying to figure out if a series converges. Just think about it for a second. If you're only adding positive numbers, it's pretty easy for that sum to just take off and run away to infinity. But here, every time you add a term, the very next one pulls you back a little. It's this constant partial cancellation that gives the series a much, much better chance of actually settling down to a single finite number. It actually makes convergence easier. And this brings us to the test itself. And honestly, it's kind of beautiful because it all boils down to just two incredibly simple conditions. So here's the deal. For an alternating series to converge, its positive part, our b sub n, just has to pass this two-part checklist. First, as you see in step 1, the terms themselves have to eventually shrink down to nothing. Their limit has to be 0. And second, step 2, the terms have to be consistently getting smaller. Each new term has to be smaller than, or at the very least equal to, the one right before it. If you can check both of those boxes, the series converges. That's it. It's that simple. But hold on. Before we jump into some examples, I have to give you a huge warning. Seriously, this is the #1 thing that trips people up, so listen close. So the crucial point is this. The alternating series test is a one-way street. It has one job, and only one job, to prove that a series converges. That's it. If the conditions for the test fail, you can't just turn around and say the series diverges because of the alternating series test. That's a major logical trap. So let's break down what happens when things go wrong. On the one hand, if condition 1 fails, if the limit of the terms isn't 0, then yes, the series diverges. But it diverges because of a more basic rule, the divergence test. Now, on the other hand, if condition 2 fails, if the terms stop getting smaller, then the alternating series test is just inconclusive. It breaks. It tells you absolutely nothing, and you have to go find a different test to use. Okay, theory is great, but let's put this thing to work. We'll start with that series we first looked at, the alternating harmonic series. All right, here's how you'd see it written out formally. First thing we do every single time is identify our bn. So we just ignore the sign flipper, which means our bn is simply 1 over n. Time for our two-part checklist. First up, does the limit of our bn 1 over n go to 0 as n gets infinitely huge? Yep, it sure does. Condition 1, pass. Okay, part 2, are the terms decreasing? Is 1 over n plus 1 always smaller than 1 over n? Absolutely. The bigger the denominator, the smaller the fraction. Condition 2, pass. Bingo. Both conditions passed with flying colors. So our verdict is crystal clear. By the alternating series test, this series converges. Okay, on to our next example. And this one is here specifically to show you what I meant about that critical warning we talked about. All right, here's our next series. We see that -1 to the n, so we know it's an alternating one. And you know the drill. First step is to grab our bn. In this case, it's n divided by n plus 1. Let's check condition 1. What's the limit of n over n plus 1 as n just blows up to infinity? Well, the top and bottom are growing at pretty much the same rate, so that limit is 1. Uh-oh. That is definitely not 0. We failed right out of the gate. And this is exactly what we were talking about before. Because the limit of the terms isn't 0, the series diverges. But, and this is the part you have to get right, you have to say it's by the divergence test, not the alternating series test. The AST didn't prove divergence, it just failed. Okay, let's tackle one last example, and in this one, checking one of the conditions isn't going to be quite as simple as just looking at it. So here, our b sub n is n divided by n squared plus 1. Now, checking the limit, you can probably tell that since the bottom grows way faster than the top, that's going to go to 0, no problem. But what about condition 2? Is it obvious that these terms are always getting smaller? It's a little tricky to see for sure.
So, when you can't just tell by looking, we get to pull out a fantastic trick from our calculus toolbox, the derivative. What we do is create a function, f of x, that matches our term's formula. Then we just take its derivative, and the result you see here is the key. We just have to figure out if it's positive or negative. Well, the denominator is squared, so it's always positive. And the numerator, 1 minus x squared, that's going to be negative for any x bigger than 1. So a negative divided by a positive is negative. And what does a negative derivative mean? It means the function is decreasing. And if the function is decreasing, our terms have to be too.
And there we have it. We've confirmed both of our conditions. The limit is 0, and we've officially proven that the terms are decreasing. So our conclusion is clear. This series converges.
All right, let's boil this all down. What are the big takeaways? First, always be on the lookout for that alternating sign. Second, grab the positive part, b sub n, and hit it with that simple two-step test. Does it go to 0, and is it decreasing? And finally, please, please, please never forget the big warning. This test is only here to prove convergence. If that limit isn't 0, it's the divergence test that gives you the final answer.
And that leaves us with one last really fascinating question to think about. We just proved that the alternating harmonic series adds up to some specific number. But what if you started shuffling the deck? What if you rearranged the order of the terms, adding the positives and negatives in a different pattern? Would you still get the same sum? The answer? Well, it's pretty wild, and it leads us directly into our very next topic. I'll see you then.